Metalloids. Metalloids are elements that possess both metallic and nonmetallic properties. Not strictly a group themselves, they are found in different groups on the right side of the periodic table, figure 1. On both sides of the zigzag line that divides the metals from the nonmetals. For example, silicon is a metalloid. It is shiny and silvery, but is not malleable and is only a partial conductor of electricity. Other metalloids are boron, germanium, arsenic, selenium, antimony, tellurium, polonium, and astatine. The electronics industry uses silicon and germanium, both semiconductors, to make microcomputer chips. You may have read about arsenic as a poison. Another metalloid, boron, is used in borax water softeners and in the antiseptic boric acid. Rows on the periodic table. The groups of elements, the columns in the periodic table, have similar physical and chemical properties. These properties, however, vary from element to element in a column. Elements beside each other in the periodic table also have similarities and gradual changes in properties. These horizontal rows of elements are called periods. The first period contains two elements, hydrogen and helium. The second period contains 8 elements, starting with lithium and ending with neon. As you go from left to right within a row, the atomic number increases and the elements gradually change from metallic lithium to non-metallic fluorine, and then finally to the noble gases, neon, at the right. Understanding concepts. Where on the periodic table do you find metals, metalloids, nonmetals, and noble gases? Define the term chemical group. Give examples of chemical groups. Compare the arrangement of electrons in the elements in the same group. Why are noble gases sometimes called inert gases? How is the electronic structure of helium different from other noble gases? Why is it still included in the group? List some similar properties of the alkali metals. What similarities in electron arrangement do the alkali metals show? Number 5. A. List similar properties of the halogens. What similarities in electron arrangement do the halogens show? Number 6. What evidence suggests the hydrogen should be in the first column of the periodic table? How is hydrogen different from other elements in the first column? Number 7. What are metalloids? 8. Rubidium is an alkali metal. What are the formulas of its compounds? With hydrogen and with oxygen. Number 9. Write the names and formulas of the 4 compounds that can be formed by combinations of potassium, lithium, chlorine, and or bromine. Express as a law the relationship between the position on the periodic table and the number of electrons in the outer orbit. Making connections. Make a chart listing practical applications of alkali metal compounds. Exploring. One meaning of the word period is a portion of time marked by some returning action or phenomenon. Determine the trends that appear across the periods of the periodic table. Is this definition appropriate? Write a paragraph giving evidence to support your view. Elemental magic. Imagine that you are visiting a sports and camping store. You are thinking of buying skates, and your friend is looking for canoes. How do you decide what to buy? Certainly, price is important. But you also have many choices of materials. The skates could be made of natural leather, a synthetic, or a combination of the two. The canoes could be made of aluminum, fiberglass, Kevlar, ABS plastic, or other substances. Scientists use the magic of chemistry to make thousands of materials. What natural or traditional materials can you see around you? The magicians are materials scientists, modern alchemists who make new products by using their knowledge of the periodic table. Understanding the arrangements of elements into groups and periods makes it possible to predict new ways of assembling atoms into molecules. Figure 1. B. What kinds of materials do material scientists use? C. What are some of the products of this magic? Over the centuries, people have used 4 general types of materials to make everything they need: metals, polymers, composites, and ceramics. The relative importance of these substances has changed over time, as you can see in Table 1. For example, in 5000 BC, metals were relatively unimportant. By 1960, they had become by far the most important materials in the world. What types of metals would have been used in 5000 BC? What types of metals were in wide use by 1960? Metals. Metals form the majority of elements in the periodic table, Figure 2. In 5000 BC, almost the only metals used were gold and copper for jewelry and containers. Because the metals were difficult to produce, they were rare and highly prized. As people discovered ways of purifying and mixing metallic elements, metal alloys such as bronze and steel became more important. They could be used for weapons, utensils, buildings, and many other uses. By the middle of the 20th century, alloys were used in everything from tractor bodies to building structures to tableware. Figure 3. Today, superalloys can be specially engineered to be, for example, heat-resistant jet engine parts or corrosion-resistant chimney linings for power plants. Why are alloys rather than elemental metals used for these highly specialized applications? Polymers. Polymers, or elastomers, are materials made of long molecules, something like miniature lengths of string. The most important elements in these substances are carbon, hydrogen, and oxygen. Figure 4. The elements of polymers materials. In 5000 BC, the only elastomers were natural compounds found in animals and plant fibers. Wool, leather, wood, linen, and cotton were used for clothing, shelter, tools, boats, and so on. Suggest other elastomers and their uses. Over the centuries, glues, rubber, and other natural elastomers were discovered. A major breakthrough in polymer chemistry was the invention of plastic polymers in Figure 5 in the 20th century, including nylon for clothing, polytetrafluoroethylene for non-stick cookware, polystyrene for drinking cups. Some new polymers are tough, light, and heat-resistant enough to be used in jet aircraft. Try to imagine a world without plastics. No CDs, no disposable food containers, no plastic toys. You can see that this book was written many years ago. They talk about CDs. The development of almost indestructible polymers is not entirely good news. What drawbacks do they have? What is being done to try to overcome these drawbacks? Ceramics and glasses. Ceramics and glasses are materials derived from minerals and rocks. The elements that are most important in these compounds include silicon, carbon, and oxygen, but many elements can be used, as you can see in Figure 6. In 5000 BC, the most important ceramics were stone for weapons, flints for tools, and pottery for containers. Glass was invented about 2,000 years ago. Today, tough new containers are being engineered that have very special properties. Figure 7. In the future, superconducting electromagnets may power high-speed trains. Carbon fiber is a ceramic. What is it used for? Why is it suitable for these uses? Composites. Composites are materials that are formed by mixing two other materials. The first composite was probably a straw-clay combination used in building bricks. When material scientists make composites, they try to combine the best properties of the polymers, ceramics, or metals that they put together. For example, fiberglass, a composite of a polymer and tiny glass fibers, can be used to insulate houses or make boat hulls. Paper is a composite. What substances might be in paper? Material science and canoes. Back in the sports store, your friend is still looking at canoes and suggests buying one for a canoe trip in northern Ontario. What kind of canoe should you use? What should the canoe be made of? Even for something as simple as a canoe, material science offers choices in all categories that you have learned about in Figure 8. Figure 8. Canoes for shooting rapids are made of different materials from those used for paddling on quiet lakes. Depending on whether you want to run rapids or just paddle on a lake, the new alchemists have given you a wide choice of materials. Research the various materials that are now used for different kinds of canoes. What are the benefits and drawbacks of each material? Having decided what kind of paddling you want to do on your imaginary canoe trip, choose the most appropriate canoe to buy. Understanding concepts. Draw a bar graph to summarize the information in Table 1. B. Examine your graph or Table 1. What types of materials were most important in 5000 BC, AD 1800, 1960, and 2000? And we'll add one, 2017. Give 5 examples of each type of material that you would use in a typical day. Polymers. Classify the polymer you choose as natural or synthetic. Ceramics, metals, composites. 3. Why are material scientists called magicians? Write a paragraph comparing them with stage magicians. Exploring. Why did metals peak in popularity and then decline? Research some aspect of the use of metals in Canada and prepare a written or oral report. Research buckyballs and other fullerenes, both named after the scientist Buckminster Fuller. How did material scientists hope to use these new molecules? Reflecting. Compare the 4 types of materials scientists use with the number of elements used. Do you think this affects manufacturing costs? Ozone, a global environmental hazard. Can elements in the periodic table occur in more than one form? Can an element be useful or helpful in some situations and harmful in others? The answer to these questions is yes, and oxygen is an example of such an element. You will recall that oxygen exists in 2 different forms, oxygen gas and ozone. The colorless, odorless oxygen gas that we breathe has the formula O2. Without this gas, all organisms would die. Ozone is a pale blue gas with the chemical formula O3. You smell this gas. If you have an electrical discharge, a spark where this smoke is produced, that pungent aroma is actually ozone. It is formed by the action of sunlight on oxygen, by lightning, and as a side effect of pollutants released from car engines. At ground level, ozone is poisonous, but in the upper atmosphere, it protects us from the sun's radiation. Ozone and sunlight. You will remember that sunlight contains many different energies of colors of light, represented by the visible spectrum. Sunlight also contains invisible ultraviolet, UV radiation, which has higher energy than any visible color. UV radiation is believed to cause skin cancer, decrease the body's resistance to diseases, and can blind unprotected eyes. It also harms plant life. Fortunately, less than 10% of the sun's UV radiation passes through the atmosphere. The reason is the ozone layer, ozone in the upper atmosphere, that absorbs the UV radiation, preventing it from reaching the ground. The ozone killer, chlorofluorocarbon, CFCs, are compounds invented by chemists in the 1930s by putting together carbon, chlorine, and fluorine atoms. CFCs seem very safe because they were stable. They didn't break down and they weren't harmful to living things. CFCs were used to clean, to cool, and to dissolve other substances. The first CFCs, Freon, is probably the coolant in your refrigerator at home. It took several decades for the first CFCs to work their way up through the atmosphere, where an unexpected reaction took place. UV radiation released chlorine atoms from the CFCs, and each chlorine atom broke apart 100,000 molecules of ozone. As the ozone broke down, the UV radiation was able to penetrate further through the atmosphere, releasing more chlorine from CFCs. As it went, figure 1, an ozone killer was on the loose. Could it be stopped? The Montreal Protocol. Recognizing the need to stop CFCs from reaching the ozone layer, over 100 countries signed the Montreal Protocol in September 1987, agreeing to cut CFC production in half by January 1996. Equipment that already contained CFCs was not banned for 3 reasons. The expense, the technology to completely replace CFCs is not yet developed. And the technology that depends on CFCs, especially the refrigeration of foods and medicine, is too important to just shut it down. Some countries have still not agreed to the Montreal Protocol. Even in countries that are not producing CFCs, there is evidence that these chemicals are being smuggled in and used illegally. The production and use of CFCs remain a global issue. Figure 2 shows the use of CFCs by region.